The science of computational fluid dynamics involves the numerical solution of the partial differential equations of fluid motion. Density contours are shown here for a solution of the flow around a cylinder. Such a numerical solution requires that the flow field domain be represented by a number of points, commonly referred to as a grid. In the surface shape and the differing length scales and complex aircraft geometries make it impractical to model the flow domain sufficiently with a single grid. Therefore, we divide the flow field into a number of zones, referred to as blocks. This idea allows very complex geometries to be modeled. The process utilized at General Dynamics to generate multiple block grid systems will now be outlined, using the F-16 forebody shown here as an example. The entire procedure can be divided into 6 distinct steps. The first step in the grid generation process involves the development of a numerical definition of the geometry to be modeled. This task is not accomplished with grid generation codes, but rather is provided to the codes as input. The database used for the F-16 forebody 4-block system is shown here. This database consists of 14 networks covering all important regions of the geometry. The next step in the grid generation process is to decompose the flow field domain into a number of block subdomains. After viewing the database generated in step 1, becoming thoroughly familiar with the geometry, and considering the flow analysis to be performed, the user first sketches the database. From here, he sketches block boundaries in an attempt to devise a suitable blocking scheme. As this procedure is not automated, the user's artistic talents and geometric reasoning are called upon. One of the most difficult aspects of domain decomposition is the representation on paper of the 3-dimensional shapes and the confusion that accompanies it. For this reason, General Dynamics has begun working on an interactive graphics code, grid block, to assist the user in determining suitable blocking strategies. In the third step, block-to-block connections and flow field boundary conditions are established. This step can be accomplished with the program Gridbound, which is a highly interactive program written for the Silicon Graphics Iris workstation. The user begins by entering the number and size of each block decided on in the first 2 steps. Pull-down menus and pop-up text windows are available for easy input. Once all blocks have been created, each is shown in computational space for clarity and may be rotated to display all 6 faces. Next, the flow solver selected for use is entered using pull-down menus. The user then proceeds to set boundary conditions on each wall of each block, consistent with the block structure developed in step 2. As each boundary condition is specified, each cell face set changes color, signifying a particular boundary condition type. When connections and BCs have been set throughout the block system, the stored information is interactively written to an external file. This is then used in the succeeding steps of the process, including surface and volume grid generation. Step number 4 in the 6-step grid generation process involves generating surface grids for each block in the multiple block system. This is accomplished through Gridgen 2D, another of the interactive codes written for Iris workstations. A block wall is created by first generating the 4 boundaries of that wall. Many methods are available for defining boundaries in both a graphical and non-graphical mode. In the current example, the far field boundary, boundary number 3, is generated graphically using an arc segment and straight line. Tracing from a database was used to define boundary number 1, the body boundary shown here. These points traced from the F-16 database are then splined to provide a continuous representation of the boundary shape, and grid points are distributed among the continuous boundary. Any of 4 different clustering functions is used to distribute a user set number of points on each sub-boundary. Here, a 2-sided stretching function is used to provide exact spacing at each end of the boundary. This process is then repeated for each of the other 3 boundaries on the wall. Provisional values to interior points are calculated using transfinite interpolation with arc length-based interpolant functions. This algebraic method often produces satisfactory interior distributions. However, several elliptic solvers are available for further refinement of interior points. Laplacian solvers, Thomas and Middlecoff schemes, Sorensen-Grape schemes, and adaptive schemes are a few examples of the available elliptic methods. We now run the elliptic solver to further distribute grid points on the interior. Here the Sorensen-Grape method is used to provide orthogonality at the boundaries. When this wall is completed, a similar procedure is used to generate the remaining 5 walls of the block under construction. The fifth step is volume grid generation, the calculation of grid points in the interior of each block. The code that has been written to accomplish this task, Gridgen 3D, is computationally intensive and runs best on a supercomputer. As in surface grids, the interior volume of each block is initialized using algebraic methods. Subsequently, refinements can be made using 3D elliptic solvers, such as the Thomas and Middlecoff method or the Sorensen method. The sixth and final step in the grid generation process is the visual verification of the complete 3D multiple block grid. This is accomplished using the program GridView 3D. GridView 3D allows the user to plot any or all of the blocks in the grid system. Also, GridView 3D allows the user to examine the planes of grid points within any block. For the upstream block of the F16 grid, these are the eta constant grid planes. This completes the grid generation process. The system of codes described here provides a visual insight into the grid system and has reduced the time required by an order of magnitude. Work is currently underway to reduce the time even further.